streaming or recording, there's no camera image that was covered. But and we'll be able to invite today.
Yeah, alright.
Cool.
Let's make a start.
Happy to
Okay, good morning everyone. Today's speaker is Shelley Gorman, Dr. Shelley Gorman. Shelley and I go way back. I first met you in 2001. She was doing her PhD on CMV and she's since then moved to Telethon Institute, where she's an independent researcher. She's working and has been working for some time now on vitamin D and the effects of vitamin D on the immune system, and she's going to tell us about her work today. Thank you, Shelley.
Thank you. Alright, I think I'm all set. So thank you very much for the invitation to speak today. I'm actually not going to be talking much about vitamin D and immunity, but more about some of our more recent work looking at the potential for solar radiation, particularly UV, to affect obesity. And this is a bit of a novel concept because it sort of switches the way we think about how we spend our time outdoors. It's usually doing exercise, but could there be any benefits from getting a bit of sun exposure as well? So today I'm just going to talk to you a bit about obesity in Australia, just to remind you about the rates of obesity, and then just go through some of the literature, the human literature in particular, about the effects of sun exposure, a bit of vitamin D, and links with obesity and cardiometabolic dysfunction. Just talk a little bit about how some of the effects of ultraviolet radiation aren't just vitamin D, there are other mediators which we think are important, and then showing you some of our experimental findings that UV can affect obesity development in mice. And finally, the mediator which we think at least has partial effect in these animal models is UV-induced nitric oxide. So we all know obesity is a big problem, and it's the abnormal or excessive fat accumulation associated with a large and increasing number of cardiometabolic diseases. And obesity in Australia, more than 60% of us are overweight or obese, and increasingly our children are affected by it too. This is the rates of obesity from 1995 to 2012, and you can see that they're gradually increasing over time. I was actually, when I went back and looked at this, quite surprised that actually it's been high for quite a while. So this is a recent publication from Lancet, where they looked at obesity in 2014 across the world, and you can see that people with orange or darker are overweight or obese. You can see it's a huge problem around the world. So the sort of ongoing thoughts behind obesity have been the sort of energy in, energy out sort of disequilibrium, but we're starting to think that it's a bit more complex than that. So there's thoughts that in utero exposures, so what mum eats during pregnancy, what mum's exposed to if she's overweight or obese, these can affect obesity development in her offspring. Then there's a role for genetics as well, and environmental exposures, including diet and activity. But what about sun exposure? So a lot of people use latitude gradients as a way of looking for the effects of sunlight on various diseases. And I'd like to say this is a latitude gradient for obesity, but it's not. This is a latitude gradient for species diversity. And you can see that in around the equator, where it's nice and warm, there's lots of UV, there's humid conditions, we see increased species diversity. So we don't actually know if there's a latitude gradient for obesity around the world, and I'm sure many of you are aware of the increased rates of obesity in some of those equatorial sort of countries. So the situation isn't clear from latitude gradient. But if we look at cardiovascular health, in particular looking in countries where people have a similar sort of lifestyle and similar sort of genetic background, you can see that, and this is a study for risk of heart disease in Europe, that there was an increased risk the further you go away from the equator. So a link with perhaps reduced UV exposure. And when they looked a bit closer in this study, they found that latitude actually was one of the highest risk factors, so more so than for smoking. People can also look at season and effects of season on obesity, and for example in Perth here, so we're down, I think this is August about here, so the UV index is now increasing, and you can see that obviously in summer we have increased exposure potentially to UV radiation. We've had a look in some children attending the obese clinics at the PMH endocrinology clinics, and they undergo a yearly glucose tolerance test, And so this is to monitor type 2 diabetes. And what we found is that those children who are measured in summer and autumn, that they have reduced glucose in response to this test, suggesting that in summer there may be a protective effect. Perhaps it's UV, or perhaps there's something else going on in summer or autumn as well. So I've got a master's student who's just starting to look back. We've got another about 250 cases now, so it'll be interesting to see whether that comes out a bit clearer. There's other seasonal studies out there as well. So this was us looking at the UV index in Japan. So there's four cities here, and you can see in summer there's increased UV index. And this study here looked at older males with type 2 diabetes, and they found that body fat percentage reduced in summer in a seasonal sort of pattern. So suggesting that there might be some effects of being summer or UV exposure on obesity or adiposity. We can also use altitude as a proxy for UV exposure, although it has lots of other different environmental exposures as well. So that's the higher you go, the more UV you get exposed to. And there's been a few studies looking at this, saying that the higher altitude you live at, this might lead to lower weight. But we also know that, for example, hypoxia can cause reduced food intake. So this can also could also contribute towards the reduced weights. And there are obviously differences in different populations who live in different altitudes as well. So it's not a clear situation from altitude. There's a very nice study that's been done in Sweden looking at sun exposure habits in women called the MISS study. So it's mainly a study of melanoma, but they looked at active sun exposure and its links to type 2 diabetes and obesity and also mortality. And they found that women who had increased sun exposure habits, so those who use sunbeds or went sunbathing during their holidays, they had a reduced risk of developing type 2 diabetes. These same women also had, those who had these active sun exposure habits had reduced proportion of them were obese, but unfortunately you can see that they also had increased exercise. So it's not easy from these human studies to really examine the effects of sun exposure and on obesity or type 2 diabetes. This is the result looking at mortality. You can see that those women with most active sun exposure had reduced mortality as well. So there are some other studies in the literature, and this is sort of looking at things the other way around. So some people have found that body mass index can determine your sunbathing habits or your likelihood to expose your skin to the sun. So in this study they found that those people with a higher BMI avoided the sun. And so this sort of puts into question about the cause of reduced sun exposure, and is there, for example, a stigma that might reduce someone's likelihood to go out into the sun. There's been a few little clinical trials, and I say little because they've been sort of about 50 to 60 in size, and in this study they looked in adults who had metabolic syndrome, and this was set in the Middle East, in Saudi Arabia, and what they did was they asked these people to go out in the sun more and take some vitamin D rich foods for 1 year, and then they tracked the metabolic syndrome rate. So it wasn't a very well controlled study. They didn't have a placebo, but they did look at their metabolic syndrome rates, and they found that after 12 months that this reduced. And then they also saw reduced rates of high triglyceride and some trends for some of these other cardiometabolic sort of risk factors as well. So suggestive of a potential benefit of sun exposure, but perhaps also they were eating better foods and they were going outside and doing more activity. So it's a bit of a confounded trial as well. Some of our colleagues in the UK have done some more controlled studies using UV phototherapy. So this is often used in psoriasis or skin conditions to reduce skin inflammation. And so this clinical trial was done by Michael Horlick in 1998, and they found that when they exposed people with mild hypertension to UVB radiation, that they found that a reduced systolic and diastolic blood pressure both during the day and at night. So this was done over about a 6-week period. So this is the study of our collaborators, and they exposed, these were young male volunteers, medical students, and they gave them just a once-off non-burning dose of UVA radiation, and found that for about 30 minutes after exposure, they saw reduced arterial blood pressure and diastolic pressure as well. But the effects weren't ongoing. And what they did find, though, that it was related to nitric oxide production. And I can go into that a bit more detail later. So there is some evidence for beneficial effects of increased sun exposure, but what's the cause and effect sort of relationship? And I think the human studies at the moment, there's not really strong evidence, and if anything, we need some more clinical trial-based results to see if there's any causal effect. And you can imagine looking at the effects of sunlight on obesity is not an easy task to do in a clinical sort of setting. Does obesity drive people indoors? And what are the links with exercise as well? And as I mentioned, the clinical trials show some benefits, but more work needs to be done. So what about vitamin D? So we know that this is mostly produced by sun exposure of our skin, and this is where the precursor 7-hydrocholesterol gets converted into vitamin D. This 25-hydroxyvitamin D is what's used to measure vitamin D status. And what are the links between vitamin D and obesity? So we know there are there's quite good evidence for associations of vitamin D deficiency with increased BMI. And in this consortium, they found for each 1 kilogram increase in BMI correlated with a 1% lower of this circulating vitamin D. Some people speculate that low levels of vitamin D could contribute towards obesity and weight gain. But some other studies suggest that obesity actually might be driving this low circulating vitamin D levels. And this might be because of various reasons. For example, vitamin D is fat soluble, so it could be sequestered away in fat. Or perhaps there's some volumetric dilution effect that's happening. But we still really don't know the reason for this. Finally, there's inconsistent results from vitamin D supplementation on obesity and type 2 diabetes and those related outcomes in clinical trials. And it could be that the clinical trials haven't been adequately designed. As yet, they're quite small, sort of about 50 to 60 in size. And quite often they start with participants who don't have vitamin D deficiency as well. So there's some more work that needs to be done in that area as well. So there is some evidence for benefits of sun exposure, but is this causal or just an association? And some of our colleagues' work suggests that it's not just vitamin D. So what we've done is tried to test a causal pathway through in vivo modelling and whether this was vitamin D dependent. And we sort of stumbled across a unique animal model to test this. So this was done through some of the work of Darryl Tan, who was an honour student from Murdoch a few years ago now. And during his studies, he was interested in, his main project was about something else, but he was looking through the literature and found that no one had actually looked at the effects of UV on serum vitamin D in mice. So what we did is we exposed the backs of our mice to UV. So these are our lamps up the top here, and we shave our mice before we expose them to UV. And we use a bank of sun lamps that typically have quite a lot of UVB in them. So what Darryl did is he initially made his mice vitamin D deficient, so he put them on a vitamin D null diet for about 4 weeks. That's about the time it takes for them to become deficient. So this study is actually done in BALB/C mice, in adult mice, and then we exposed the mice to either two doses of UVB radiation, which are in the erythemal range, so cause a mild burn. And what we found was that it was only the female mice that could respond and increase their serum vitamin D levels after UV radiation. So you can see there's sort of like a dose-dependent effect. The higher dose results in high levels of 25-hydroxyvitamin D, but there was really no effect in our male mice. We tried different radiation schedules and ongoing, and really didn't see any effect in the male mice. That's quite a curious finding, and we looked a bit further at some of the metabolites and found that skin levels of the precursor 7-dehydrocholesterol were reduced in our male vitamin D deficient mice, so suggesting they had less of the precursor to be converted into the vitamin D. And then we looked further downstream as well in the kidneys and found that the vitamin D deficient male mice had increased levels of this enzyme. So this CYP24A1 is the enzyme that breaks down the active 125 and into inactive levels. So perhaps there's less of it to start off with, and then it gets turned over at a faster rate as well. But at any rate, this allows us to have a look at some of the sort of vitamin D independent effects of UV, because our mice can't increase their circulating levels post UV irradiation, and so any effects that we observe would be largely vitamin D independent. And this is a unique model because most of the animal models looking at the sort of causal effects in the vitamin D pathway use vitamin D receptor null mice, which have lots of problems. They're often rachitic and you have to give them a rescue diet. And there are other similar models out there as well. But this allows us to not worry so much about some of these other defects. So then this brings me to some of Sian's work. So Sian did her studies a couple of years ago, and she was looking at comparing the effects of ongoing UV exposure with vitamin D on obesity development. So she did a quite amazing experiment for an honours student. So she started off by feeding mice either a low-fat diet with or without vitamin D. So this was to make them vitamin D deficient down here. So we did that for 4 weeks, and then from 8 weeks of age, we then divided them into 4 further groups. So continued on the vitamin D, or were not supplemented with vitamin D, and then some mice were given a high-fat or low-fat, continued on a low-fat diet. So we fed the mice a high-fat diet to induce weight gain and cause metabolic dysfunction, and they were fed these diets for a further 12 weeks until they were 20 weeks of age. These were male black 6 mice, and so these mice are susceptible to developing obesity. So we then further divided the mice, and you can see this is where it gets a little bit complex. We had 12 treatment groups, and mice who received no UV or a suberythemal dose of UV radiation, so twice a week, 1 kilojoule of UVB radiation, or they were given fortnightly erythemal UV radiation. And so then we looked at a number of outcomes. So we looked at weight gain throughout this time period, and then also adipokines, glucose tolerance, all of these outcomes here over the time course. So first of all, we looked at circulating vitamin D. So just to confirm, we found that feeding the mice the low-fat diet without vitamin D reduced the circulating levels of vitamin D, so that was good, as expected. Then we saw an unexpected finding. So if we gave our mice the high-fat diet, you can see that the levels of vitamin D increased. So our high-fat diet contains lard, so we think there might be some animal products in there which have some vitamin D. So this was a little bit unexpected, but this was all right in the sense that UV irradiation didn't change the circulating levels of vitamin D at all. In the mice given the high-fat diet supplemented further with vitamin D, we saw an increase, a little bit of an increase in the circulating vitamin D levels, but no real effect of UV, just a sort of a very transient effect over here. So the real finding of these studies was that UV radiation suppressed weight gain. So these are the results here. We've got high-fat diet given to the mice up here with and without vitamin D. You can see there's no effect of the vitamin D further supplementation. But if we gave this suberythemal or erythemal, so non-burning and burning, we found that about a 30 to 40 to 50% reduction in weight gain over this 12 weeks. If you compare it to low-fat diet, so these black mice put on weight quite well, even on a low-fat diet, you can see that this is where you see that the 30 to 50% reduction. And we actually did see an effect in the low-fat diet, which were given this high dose of UV. Another interesting finding was that when we gave vitamin D on top of the UV, we didn't see the effects on weight gain. And I actually really struggled to explain why this might happen. So if anyone has some ideas, that would be great. Perhaps there's some sort of interaction of vitamin D with other UV-induced mediators, or maybe it's something to do with the male mice turning over the vitamin D, and if you give more, just something happens. But I can't explain that at all. We did see, as you would expect, if the mice aren't gaining weight, less white adipose tissue in the UV-irradiated mice. But again, UV didn't suppress in the mice given vitamin D supplemented diet. So we did a glucose tolerance test in the mice. So in this, mice were fasted for 5 hours, and then we gave them an intraperitoneal shot of glucose and then measured their glucose levels over time. So in this assay, what you would expect is mice fed a high-fat diet who have some signs of glucose intolerance will increase their glucose levels, and then this will slowly decrease over time, and the response is much reduced in the low-fat diet-fed mice. So we didn't see an effect of vitamin D. So this is these results here, the high-fat diet and the low-fat diet over here. But when we looked at the effects of UV, you can see that either UV treatment significantly reduced this level of glucose intolerance by about 50% in comparison to the low-fat diet down here. Again, we didn't see any effect in the mice further supplemented with vitamin D. And we saw similar effects for insulin resistance, fasting glucose, and also insulin. We also had a look in the livers for the presence of fat, so steatosis. So this is a liver from mice fed a low-fat diet, and this is a high-fat diet. You can see there's all these little pockets of fat in the cells and between the cells. We did see an effect of vitamin D in these studies. So you can see this is the vitamin D fed mouse, and there's much reduced liver steatosis there. And UV had also an effect, and it was much more marked than the vitamin D. So this is the no UV high-fat diet. We saw this is the suberythemal dose, and then the erythemal dose, and this is almost as good as a low-fat diet only. So this is a histopathology score which we generated, and you can see that the effects of UV were much more than the effects of vitamin D alone, and quite similar to the low-fat diet down here. So we found that UV suppressed the development of obesity, signs of weight gain and metabolic dysfunction. This was independent of vitamin D status, and we found that the low dose of UV was quite effective. There was limited or no effect on some other markers, so we didn't really see any changes in adipokines or circulating pro-inflammatory mediators, or on circulating fats as well. Some of the effects of vitamin D were really just limited to liver steatosis. And we saw this strange finding where if you gave vitamin D as well as UV, it inhibited the effects of UV radiation. So we've now gone on to have a look at mechanisms, so looking to see what mediator induced by UV is not vitamin D, what mediator could be responsible. And so I've already introduced this. We're interested in UV-induced nitric oxide. So there's quite a lot of literature out there that suggests that nitric oxide is great for endothelial cell function, for perhaps reducing hypertension, and also for controlling obesity development. It can inhibit insulin resistance and also regulate heat production or thermogenesis in brown adipose tissue. Our colleagues in the UK have found that UV releases nitric oxide from skin, so there are preformed levels of nitric oxide trapped in the skin, and this was associated with that reduction of blood pressure in those medical students. So this is sort of their hypothesis at the moment. There's not actually much known about this pathway, but it's thought that sunlight results in the release of bound nitric oxide scores and the export of a nitric oxide-like bioactivity. And they find increased levels of nitrite in the blood after UV exposure. So we wanted to do something similar in our mice as well. So we got this assay up and running using the IVIS bioimager in the institute, and what we did was we patented a chemical which fluoresces when nitric oxide is present. It's DAF2DA, and you can see in mice exposed to UV or to SNAP, which is a nitric oxide donor, we found that we saw some fluorescence in the skin. So this was quantified in terms of photons per second, and this was measured, I think it was about 5 minutes after UV exposure, so it didn't take long for the nitric oxide to be induced. This is was done in about 5 to 6 mice per group, and you can see this is for mice fed a high-fat diet. It was at the end of the 12-week sort of time course, but UV increased the levels of nitric oxide, as is the nitric oxide donor, and this one down here was given immediately after UV, and it's a nitric oxide scavenger, and you can see the effects were completely reversed. So we did an experiment, a nitric oxide experiment, and it was the same sort of study. We gave mice the low-fat diet for 4 weeks, and then gave them the high-fat diet for 12 weeks, and we gave them the UV as before, but also this nitric oxide donor, to see if we could mimic the effects of UV exposure, and then the nitric oxide scavenger after UV to see if we could block the effects of UV radiation. Again, we looked at all these outcomes and only saw an effect on fasting glucose and hepatic steatosis. And these are the results. So you can see that UV suppressed again this fasting glucose, and we saw a reversal of this in mice given this CPTO as well. And then we've got this liver steatosis. This was the histopathology score. Again, UV suppressed. This time the nitric oxide donor suppressed, and it was reversed by the nitric oxide scavenger. So suggesting that nitric oxide induced by UV is having some effect, but it's not the whole story. Okay, so last year Naomi came along and she was, I was, and I got her to do this study, so interested in the effects of UV in overweight mice. So what Naomi did is she fed the mice a high-fat diet for 6 weeks to induce some weight gain and then some signs of cardiometabolic dysfunction, and then we started the UV protocol. So this was to see whether you could sort of intervene in the progression from overweight to obesity. Naomi did a couple of extra things. So we compared the effects of our lamps with some other lamps that we've got, the Clio sun lamps, and these have been used in tanning parlours, and they contain much less UVB and a lot more UVA. So Naomi gave the same low dose, so the suberythemal dose of UVB, but these mice received a lot more UVA than these ones over here. But this spectrum of light is much more similar to what we would receive if we go out into the sun. So the results I'm showing you for this are the fasting insulin, weight gain, cholesterol and hepatic steatosis, because these are where we saw a significant effect. So Naomi fed the mice first of all for 6 weeks and saw significant weight gain after 6 weeks, which was good to see. And she did see a reduction in UV if she gave this FS40 UV radiation, but you can see the effects weren't as great as before. And we didn't see an effect with this other UV source. We saw sort of a partial but not quite significant reversal. I think statistically it's almost there in the nitric oxide scavenger CPTO as well. Interesting finding was that with these UVA containing lamps or UVA rich lamps, we saw a reduction in LDL cholesterol, which we didn't see before, suggesting that UVA might be doing some different things to UVB. With both UV sources, we saw a reduction in this liver steatosis. So with this FS40 and with this Clio, and we saw a bit of an interesting finding with the low-fat diet here. I can talk about that later if anyone wants to. And then a complete reversal with this nitric oxide scavenger as well. So this is consistent with the effect of the nitric oxide induced by UV effects on the hepatic health. We also saw significant reductions in fasting insulin as well. So that was, and this was with both of the UVs. So our results suggest that UV can suppress signs of obesity and cardiometabolic disease, and that nitric oxide might be important for regulating fasting glucose and liver steatosis. There might be some benefits in already overweight mice, and I think these studies suggest there is a role for other UV-induced mediators, and this is what we'd like to have a look at in the future. But before we do that, I'm quite interested in what's the potential for adipose tissue. So this tissue is really important for heat production, specifically in infants. And we've known for quite some time that infants have high levels of brown adipose tissue, and it's responsible for that non-shivering thermogenesis to keep the babies warm. But perhaps in the last 10 years, there's been a rediscovery of brown adipose tissue in human adults, particularly around the sort of the neck region. And you can imagine that this is quite, well, beneath the skin, which we might get quite a bit of UV exposure around our neck and our neck region. So in the mouse, there's also quite a nice deposit of brown adipose tissue, and this is directly beneath the site that we UV irradiate. So it seems to be a potential organ which could be stimulated by UV, and that's what we're having a look at the moment. We've imported this mouse called the thermo mouse, and it's quite a cool mouse where if you, it's got this UCP1, which is the uncoupled protein 1, and it's got a luciferase marker right next to it. So under certain conditions, you can get the mice sort of light up under the IVIS bioimager. So this study here, they put the mice in the cold, and you can see quite a nice increase in expression of UCP1 in the brown adipose tissue. So this is just the pathway of the UCP1, which bypasses the respiratory chain to produce heat. And we've done some preliminary investigations in our mice, and we do see after 24 hours increased expression of UCP1 in brown adipose tissue, which is quite reassuring. And this is just quantified in about 8 mice, 24 hours after exposure. I'm also quite interested in, because obviously there's an important link with mitochondria as well, so we're looking to quantify mitochondria in the brown adipose tissue using some of the MitoSpy products. And there's two MitoSpy, green and orange, and one quantifies the numbers, and this orange looks at the membrane potential. So we've been doing this by confocal, and this is our control. I'm sorry if you can't see all that well, but the orange, these are the little daffy stained, and these are the orange. You can see a little bit there of as well. Oh, that's great, thanks Alex. And then this is the UV, and you can see there is increased expression, but I've done this in one mouse per group, so this is a bit of interesting preliminary data. Doing some more work on that tomorrow. So that's quite exciting. We're redoing this nitric oxide experiment in thermomice as well, and so that will be really interesting to see how it goes. We do see an effect so far of UV radiation, so that's a relief. It's a different mouse strain. It's not the BLAT6, it's a FVB mouse, which they're interesting mice to use. And we're looking at ongoing weight gain and all these other outcomes as well. And one of the other things I'm interested in is the immune cells in the brown adipose tissue. So there's actually not much known about brown adipose tissue. A lot of the assumptions are that white adipose tissue immunity is similar to brown adipose tissue, but we know there's a lot more mitochondria and a lot more vascularity in the brown adipose tissue. So it could be quite interesting to have a look and see what cells are there. There's some studies though, and what they have found is that the immune cell profile changes after 8 weeks of feeding BLAT6 mice a high-fat diet in this tissue, that they have a unique population of Treg cells, and that these Treg cells, we know from other studies, are important for mediating insulin tolerance through white adipose tissue. So what is the function of these cells in here? That would be quite interesting studies to do. There's some other studies looking at cold exposure and finding that it recruits M2 macrophages through an interleukin-4 dependent mechanism. But there's some controversy about the phenotype of macrophages. I think that's just normal in mice fed a high-fat diet. And similar effects in white adipose tissue as well. And so I've just started having a look in the brown adipose tissue, and we do see increased expression over here of CD301, which is one of those markers of M2 macrophages 24 hours after UV exposure. So that's in the blue here. So again, these are quite preliminary, but I think perhaps starting to tell a story about UV having an effect on the immune, mitochondrial, and perhaps thermogenesis pathways. So I also mentioned I'm interested in other UV-induced mediators. So some of these could include alpha-melanocyte stimulating hormone and beta endorphin. So these are both increased after UV exposure, and are kind of the yin and yang of food society. So one, alpha-melanocyte stimulating hormone reduces food intake, whilst beta endorphin increases it. So I think that would be quite interesting pathways to examine. We do find increased alpha-melanocyte stimulating hormone in the blood of our UV-exposed mice. And we're also quite interested in interleukin-6 because that's produced in the skin after UV exposure, and it's also important in muscle for as part of activity. It's increased in muscle and related to reducing insulin resistance as well. So I think that would be an interesting pathway to have a look at. So these are some other things we're interested in doing as well, but I just need a bit more money. So this just leaves me to acknowledge all of my colleagues, particularly some of the students who have been working on the projects, and also collaborators and funding. Thank you.
Thanks, Shelley. Questions?
Thanks for that talk. That was a very interesting report. I haven't often got to listen to a lot of UV work, so that's great. Question for if the brown adipose tissue thinks that might be kind of the way to go. I'm not sure if it's unethical, but can you get mice that don't have either sub-optimal or no brown adipose tissue, and then kind of see if they've still got that effect of the vitamin D and fat diets?
Yeah, so people do brown adipose tissue transplants. There's been some nice studies where they've transferred, I think it's brown adipose tissue from fat mice into skinny mice, and shown that they also transfer insulin resistance with it as well. So you could take it out as well and see what happens. I think that's a good idea. I actually have had something similar in my grant a few years ago, so good idea.
So as a follow-up to that, is there a difference in the brown adipose tissue between males and females in the mice? Or?
I don't know if anyone's done that.
Yeah. the differences in humans as well.
Yeah, so we haven't done any of our studies in female mice,
Yeah.
and I think that would be good to do. Female mice are more resistant to the effects of high-fat diet than the male, so people tend to use the male. But we have done some other studies looking at feeding female mice a high-fat diet and then looking at some of the in utero effects in other models, and then you can make them fat, they just don't get as quite extreme sort of phenotype. But brown adipose tissue, I don't think anyone knows as yet.
Yeah, has there been any work done looking at the effects of administering nitric oxide in low doses over a long time frame, if that has any effect on metabolism or obesity?
In humans or mice?
Or either.
So there's quite a lot of work that's been done in that area. People quite often use L-arginase, which is sort of produces nitric oxide, but a lot of other things as well, and they do see benefits. Quite often they can use an inhibitor of the nitric oxide pathway, and a bit like the SNAP, so a bit like the CPTO, and yeah, there's quite a lot of pretty strong evidence in rodent models. In humans, it's a little more sketchy. There's a bit of a reluctance to give nitric oxide or nitrite or nitrite to people because it's associated with carcinogenesis in some other situations, especially in Europe. There's quite a low sort of dose height, well, I can't quite think of the word, that's allowed in European water sources, for example. So there's been a couple of studies looking at nitric oxide, some administration in some form or another, and they've seen benefits, but it's pretty early days and the studies are quite small.
Okay. So, could you please tell me the actual wavelength in UVA and UVB irradiation?
Yeah. So UVB is usually between 290 and 310 or 315, depending on your definition. So FS40 lamps are all around that 308 nanometers, and then UVA is from sort of 310, 315 all the way up to 400 nanometers.
And also it's interesting finding, but the UV irradiation, does it really support in the context of Australia, where we see a higher obesity rate, and also in the Middle East we have high incidence of UV radiation, but it doesn't really support what you hypothesize here.
I think that's fair enough.
We should be less obese to support what you showed there.
But I think you've got to consider our changing lifestyles as well in Australia over the last 30 years. We're much more indoor than we used to be. We're much more sun conscious. We do protect our skin a lot more. When we go out in the sun, we usually cover up. Not everyone does. And I think there's more than just UV, obviously. There's a whole lot of other factors going on. And I didn't mean to say that UV was everything, but I think it could be part of a package that you go outdoors, get a bit of sun, not too much, and then you also do your exercise as well, and that's where you can get your benefits from. In the Middle East, there's a lot of evidence that the obesity rates are increasing in the Middle East, but again, there's a lot of cultural practices of covering skin up, and while there is a lot of UV, people might not be actually exposed to much UV. And I think there's also issues around genetics, and we have no idea from our mouse studies as yet what the genetic sort of, is there a susceptibility towards the UV effect as yet. And again, maybe in people with more darker pigmented skin, there's a preventative effect of having melanin in the skin from any of the beneficial effects of UV, but we don't know that at all.
That was going to be my question, was the effect of skin colour.
Yeah.
And somehow you're going to have to find a balance of what's healthy sun exposure and what is going to predispose you to skin cancer and melanoma, and it's going to be difficult.
Yeah.
But I was going to ask that question about the effect of skin colour.
Yeah, I think we're trying to focus on low dose UV and low frequent exposures, so hopefully that won't predispose most people towards skin cancer, and but that's the other.
And is there a difference in the proportion of UVA and UVB in sunlight over the course of the day? Has anybody looked at that? So, would early morning sun be better than, midday sun?
Yeah, well, I think I don't actually know the answer for the proportion changing over time, but a lot of people, especially people who say to get your vitamin D through UV exposure, suggest you actually should go out in the middle of the day. and expose more of your skin for a shorter period of time, because that's actually safer, because you won't get any of the benefits early in the morning because there's not much UV, because the UV index is all UVB rated, so that's peaks in the middle of the day. So, you know, we should all go sunbathing for 5 minutes, nudie, and get our vitamin D, and nitroxide and other things that way, but no one wants to do that in winter.
This is more of a generic question in terms of, you know, you showed vitamin D counteracting the effect of UVB. A lot of people now on the supplements for vitamin D that we're taking, and if you're exposing, so you're not really seeing the benefit of either of them, or how does that work?
I don't know if we can really translate that from the mouse study directly into humans. I have a sneaking suspicion it's a male mouse phenomenon, that vitamin D preventing the UV effects. And I don't think anyone's done any trials that have compared UV, vitamin D, UV plus vitamin D, so it's really hard to quantify that. And, yeah.
Okay, no more questions. Thank you much.
Thank you.